Hey, welcome back AP Calculus students. Today we're looking at 7.3 anti-differentiation by parts. Now, in the hierarchy of doing antiderivatives, what we're trying to look for is if we can do it, our antiderivative from one of the rules or cheat sheet, that's what we're going to try to do first. If those don't work or don't apply, then what we're going to do is we're going to try to U sub. And lastly, if we can't do either the cheat sheet stuff or the U sub stuff, then we're going to try to do this next strategy, which is anti-differentiation by parts. Now, I'm not too sure if they're going to have any anti-differentiation by parts on your exam at the end of the course, but it's good to know. All right, so it looks like the integral of u dv is equal to uv minus the integral of v du. So if we look at the first problem, we have the integral of x cosine x dx. Now, we definitely don't have that on our cheat sheet, and this is not a u sub type problem where we have an inside outside. Excuse me. So this is a giveaway that we're trying to anti-differentiate by parts. So this little side note here that I put, it says let u equal something that will derive out eventually. So we have to have a u and a dv here. So I'm going to say that my x is my u, and cosine x dx would be my dv. Okay, so it's going to look like this. So when I do this, let's do the du. That would be just, whoops. Du is 1. And then our v, right? So we have cosine x dx. So v would be the antiderivative of cosine x, which is negative sine x. Okay, so we're going to find the du, and we're going to find the v from our u and dv, and then we're going to make it look like the right hand side of our equation. So we're going to have uv, so x times negative sine x. So negative x sine x is our uv. And then we have to do our integral of v du. So we have v du sine x times 1. Right, du is 1. I should probably say dx, right? Dx. Okay, so this is our negative v du. Oops, I forgot a negative there. Okay, so let's simplify this a little bit. You don't have to do this step, but it just helps because the negative is going to be a plus, and then sine x dx. So the integral of sine x dx is negative cosine, right? Negative cosine. Sine is negative cosine. Yep, so we're going to have negative x sine x plus, we're going to do this thing, which is negative cosine x. At that point, we'll be done. All right, so the key here is we have to make sure that our u will derive out eventually. Now, we're going to get into some examples later on where we don't have the option to let the u derive out. But yeah, it'll make more sense when we get there. Okay, so for our second one, our u is going to be x squared, because we know if we keep deriving x squared, we're eventually going to get to a point where we're not going to have any more x's. Now, that wouldn't work for e, right? Because e is itself, so we're just going to have e to the x over and over again. So we don't want the e to the x to be our u. So our u is x squared. Our dv is e to the x dx. Our derivative of u would be 2x dx. And then our v would be e to the x. Right, the antiderivative of e to the x is e to the x. Okay, so we're going to set this up. uv minus the integral of v du. Okay, let's just switch colors here. So we have uv, so x squared e to the x is uv minus the integral of v du. So v e to the x times 2x dx. Okay, so now we're going to integrate this again. But again, we're going to do this using anti-differentiation by parts. So this part's not going to change. But here, our u is 2x, our dv is e to the x dx. Okay, so du equals 2 dx, and v is equal to e to the x again. So we're going to repeat this process. Don't forget that x squared, e to the x, minus, and then we're going to replace this thing with the uv minus integral v du. So u is this time 2x times v is e to the x, and then minus the integral of v du, so e to the x, or 2e to the x dx, right? Du is 2. Okay, notice I'm putting brackets around it because we're subtracting that whole thing, right? It's minus this whole thing. So whatever we do to that, we just got to keep expanding it. Okay, so we can actually do this one. The integral of 2e to the x dx is 2e to the x dx. So we have x squared e to the x minus 2x e to the x, and then minus negative is going to be plus 2e to the x. And we should probably put a plus c here, right? Because that'll represent any of the different antiderivatives, or I should say functions whose antiderivative is that, or derivative is that. Okay, so we're done. So this is a two-step, right? We have to do integration, anti-differentiation by parts once and then twice in order to get our answer. And then sometimes you might do it multiple times. But yeah, as long as you understand that we're just plugging it into our, well, it's not a formula, but it's just a rule. So u dv equals uv minus integral of v du. Okay, so this is one of them where it's kind of funky because e to the x is not going to derive out, and if we do the derivative of cosine x, it just keeps going back and forth between cosines and sines. So let's go ahead and see what happens here, because there's a little trick here. Let's say that u is the cosine, and then let's say that the dv is e to the x dx. Okay, so then our du would be, derivative of cosine is negative sine x, and then v would be e to the x. Okay, so we're going to plug it in here. uv is e to the x cosine x minus the integral of v du, so e to the x, or negative e to the x sine x. Okay, we can clean this up a little bit. We'll take that minus negative and make it plus. And then with this part here, we're going to do the same thing. This time our u is going to be, let's change colors here. Our u is going to be, our u is going to be sine x. So u is sine x. Du is e to the x dx. Our du is going to be cosine x. And then our, this is v. Our v is going to be e to the x. Okay, so we're going to repeat this process again. So we have e to the x cosine x plus, and then we're going to do this thing as our right side of our form, right? So then u is sine x, v is e to the x. So e to the x sine x is our uv minus the integral of v du. So e to the x cosine x. Cosine x dx. Now notice that this thing is exactly what we started with, right? So let's say that this, right, we're trying to find this integral e to the x cosine x dx, right? So we're saying that that's equal to the whole right side. This is what we started off with. Okay, because this is the same as what we started off with, we can solve this algebraically. We can treat that whole integral of e to the x cosine x dx as one thing. I'm going to add it to both sides. Oops, we don't need that equals. Okay, and what's going to happen is the minus and the plus, they cancel out, right? And then on the left-hand side, what we have is 2, right? 1 plus 1 is 2. Integral e to the x cosine x dx equals this whole side, e to the x cosine x plus e to the x sine x, and then divide by 2. Okay, so now we have solved it, right? We have that thing that we're trying to look for, e to the x cosine x dx, is equal to the right-hand side. So it's solved. Okay, some of you guys might have asked, all right, we had an e to the x cosine x here. Why couldn't we do it earlier? And that's because this doesn't have an integral in front of it, right? If there were the integral sign in front of it, we could definitely start doing our algebra from there. However, we didn't. We only had it at this point. Okay, so one of the more difficult ones to solve, but definitely doable if you are looking for the right thing. If we're looking for, oh wait, I know that if I have the same exact integral as I'm solving by anti-differentiating by parts, then I can use my algebra to solve. Okay, and then on to the last one, we're looking at the integral of ln x dx. Now, this one's a little bit more difficult, and it's tricky as well because we don't really have a u and a dv. Well, we could, but we really don't. And the thing is that usually we do our u as our thing that would derive out, like our dx, but that would be weird. So in this case, we're going to say that, whoops, u is equal to dx. And v is equal to ln x. And then when we do this, dv is ln x. And as we do this, then it should come out pretty nicely. Wait, let me just check this in my brain. Actually, no. Let's go back. Let's say that u is ln x because ln x has a derivative, right? Which is 1 over x. Yeah, okay, so then u is ln x, which is not going to derive out, but yeah, it will work out in the end. So dv would be our dx. Okay, so our du is 1 over x, and then our v would be x. This should have a dx on it. Okay, so if we're doing our anti-differentiation by parts, then we know that the integral of u dv is equal to uv minus integral v du. Okay, so let's put this all in, and you'll see that it comes out pretty nicely. So we have u dv, uv, sorry, is ln x times x, so x ln x, that's the uv. And then we're going to do minus v du. So v is x, and du is 1 over x. So the nice thing about x times 1 over x, the x's cancel. That's just 1. So the integral of 1 dx, or even just dx. Okay, so the integral of 1, that's nice and easy, that's x. So the whole thing here is just x ln x minus x. Okay, so yeah, a little bit tricky because this really only has one thing, right? Ln x. It does have the dx, and then we have to decide which one we want to do. And if you need to, you can trial and error, right? You could have just said that, okay, u is the dx and dv is the ln x, and seeing that that probably wasn't going to go anywhere, and then go back and redo it the other way, and then you should come out with the right answer. Okay, again, this stuff is maybe going to be on your end of course exam, but I wouldn't worry about it too much. It's just good practice and good knowing how to do this stuff if we can't do our cheat sheet rules or our u substitutions. Okay, good job.